So today we're going to continue with distinct elements, and I'm going to do the details of the algorithm by Baryosef, Jairam, Kumar, Sivakumar, and Trevisan. So just to recall, we discussed, the hyperlog-log, or rather the basis of the log-log algorithm last time, the probabilistic counting idea. And what I'm now going to describe is an improvement by Baryosef et al. Now, this is an improvement that is really, it's a theoretical improvement, because in practice, what Flageolet-Martin showed was essentially the probabilistic counting algorithm can be made eminently practical. And so what Baryosef et al. Gave is a 1 plus epsilon approximation to the number of distinct elements. And the storage is going to be in the realistic model. So if you assume access to truly random hash functions, then what you can get is an epsilon to the -2 log n, and you get a 1 plus epsilon approximation. What we proved what we proved for probabilistic counting was just that you could get a constant factor approximation. That's what we could prove. And here you get a provable bound of a 1 plus epsilon approximation with an epsilon to the -2 in the runtime. And so the idea is really neat. So it's based on the probabilistic counting idea. So remember, in the probabilistic counting, just to recall, so for every element I, we have this Ri. So Ri is the largest number of trailing zeros in the hash function. So you apply a hash function and you look at the number of trailing zeros, and the log-log, the probabilistic counting algorithm, would essentially just track the largest such value, and it would simply store that. Instead, the idea here is to be able to get a 1 plus epsilon approximation, you need some kind of concentration. And that concentration is achieved by, instead of storing the largest, you store a smaller value such that sufficiently many I have Ri greater than R, and this will ensure better convergence, or rather, maybe instead of convergence, I should say it ensures better approximation. So feel free to stop me at any point, at least especially in the beginning, if you want me to go over any details, because I'll be talking about sort of what I did towards the end of last lecture.
Just a quick question. The previous one, the probabilistic counting, so is it like impossible to get concentration bounds enough to get a 1 plus something approximation, or do we just didn't do the analysis for it?
It is possible to get sharper bounds on the variance, but it's extremely complicated. I mean, it requires a lot of complex analysis just to be able to just understand the expectation of the estimate. But you can get the expectation. There have been subsequent analyses by Flageolet-Martin, or by Flageolet and co-authors, where they were able to give even, like, they could bound the variance. I don't recall there explicitly being sort of a Chernoff type tail concentration bound, but that might be possible as well. Of course, the reason to not go into that is, again, that it would require us to really go into a lot of complex analysis to understand their analysis. Also, I think that there are lots of ideas in this result which I think are really instructive, especially to understand how one wields the Chernoff bounds and different techniques regarding hashing as well. And you'll see that a lot of the ideas that we've talked about in the past will appear. Okay, so yes.
I'm still wondering, like, when would you want to use this algorithm?
You mean counting distinct elements?
Yeah.
So, for example, one place where it would be used is if in a web server you're tracking, like, how many distinct users or how many distinct IP addresses have connected. Then you could maintain this small sketch as opposed to storing the entire list of who was connected. I myself have used this essentially in some kind of a graph problem where, you know, for some high degree vertex, let's say you want to basically just keep track of the degree of the vertex, except your graph is dynamically changing. And so there are certain edges that might be repeated. So you might think of a social network where there are basically like some kind of communication, maybe like a post or, you know, a chat or something like that. And you want to track how many distinct people someone has chatted with. And especially when these numbers are large, it's extremely useful to have a very short sketch, because you want to run the sketch on every vertex simultaneously. And so essentially the ability to do this with something like a 1 kilobyte sketch per vertex when you have maybe like millions of vertices is extremely powerful.
Sure, that makes sense.
Yeah. So these are two examples, but if you actually even just search for hyperloglog, you'll see that there are tons of blog posts on it by data science practitioners, and a lot of discussion about how to implement the algorithm. The analysis, of course, even the analysis that I showed over here is something that is not often seen, and the actual analysis using complex analysis, I mean, that is really, I don't think there are many people who sort of go into that. But the fact that it's implemented in pretty much most large data science companies have or use an implementation of the hyperloglog. So it's considered a very fundamental problem in streaming. And this is really one of those places where, you know, analysis of algorithms and randomized algorithms have actually made a direct impact on practice. Okay, so back to the Barrios-F et al. Algorithm. So we're going to use two hash functions here. H is going to be a hash function as before, and this is going to be used to define Ri, the number of the number of trailing zeros in the hash representation. We're going to use another hash function called G. This is really a space-saving trick. It's not so much an issue of you'll see that it's essentially, I'm going to use this hash function because it's too expensive to store elements explicitly, and I'm going to use this hash value under G. So what G does is it's sort of reductive, right? It maps the universe into a much smaller universe. So it maps elements to a random string of essentially log of epsilon to the -4 log square n bits, right? So the universe is going to be reduced, which means you'll have collisions. Whereas this hash function is not reductive, right? So you expect it to sort of uniformly spread things around. I mean, this will do that as well, but multiple elements will be hashed to the same value. We'll also see that this analysis only requires pairwise independence, which is nice, and I'll come back to this at a point. Okay, so what is the actual algorithm itself? So the algorithm is going to be a set, and that set is going to be called B, and there's going to be a value Z as before. B is going to store all elements I such that Ri is greater than Z, and that's all that's going to be there, right? It's going to store all elements so that Ri is greater than Z. Now, instead of storing the elements, it's going to store the hash value under G. Okay, so how do we process an element? If Ri is greater than Z, which means that the number of trailing zeros was more than Z, where Z is this threshold that we're maintaining, we are now going to add I to our bucket, to B. Except how do we add it? We actually compute the hash value. We compute the hash value. We'll also keep track of Ri because, you know, we have lost I. We're only going to store the hash value, so we won't get R of I. And R of I is computed with respect to H, not G. So we're going to add this to the bucket. Now we're taking a union, which means if I has appeared before, nothing is going to change. There is also the issue that you could have two different I and I prime such that these quantities are the same, in which case you've lost that information, and we'll discuss this shortly. Now, what we're now going to do is, so we keep sort of, you know, adding these buckets to pairs to B. If B becomes too large, we will reduce its size. So how will we reduce the size? So suppose B crosses some size threshold, C over epsilon square. We are now going to increment Z, and we're going to remove all pairs such that Rj is strictly less than Z. So you go over all the pairs, you remove everything was less than Z. and you increment z. You do this, you keep doing this until b is going to be at most is strictly less than c over epsilon square. What is output in the end is 2 to the z. That was what the the probabilistic counting algorithm did. And we're just going to multiply that by the size of the bucket. And this is going to be crucial to get the sort of concentration that we need. Okay, and the storage, remember, is b times the size of the number of bits to store every element of b. So b is at most c over epsilon square. How many bits do we need to actually store an element of b? So we need to store g of I and r of I. And r of I is going to be at most log n. And this is essentially what we had in the probabilistic counting. G of I, recall, is only going to be log of these many bits. So again, it's log n plus log 1 over epsilon. And so we get 1 over epsilon square log 1 over epsilon square, log 1 over epsilon, and a 1 over epsilon square times log n, right? So what we get is essentially O of 1 over epsilon square log 1 over epsilon plus log n. This is what we get in the end. So this is the storage as promised. Any questions about the algorithm itself? Any questions about the algorithm?
Quick question.
Yes.
When we have that set union for b inside the loop,
Yes.
That seems like an expensive operation. Could you elaborate on that?
This, you could just store this as store the set as a hash table.
Oh, right. Okay, never mind then. Yeah.
Right. So this is cheap. Store the set as a hash table. You might be a little worried about this part, that how do you remove these? And if if you're worried about that, you could imagine storing the set not as a hash table, but as, let's say, a balanced binary search tree with Ri as the key. Right? So you could use Ri stored as a binary search tree, or you could basically even store these. Actually, no. Let's keep it even simpler, right? Store a collection of lists for each value of Ri, and each of those lists could be stored even just as a linked list. Well, no, maybe you need a hash table. Sorry. So each of those lists you store as a hash table, and you can do all of these operations fairly efficiently. In any case, the size of the set is really small. So in the worst case, you could even go over everything. So. But you're right that now what you're asking is a valid question practically. Asymptotically, it's not that important, but in practice, it is important. And in practice, one of the benefits of probabilistic counting is that the operations are so simple that they can be basically done by machine instructions, just by some bit magic. And this tends to be more involved in terms of data structures. So that is a valid point in practice. Okay. Now, what I'm going to assume, let's just say at any point there are, okay, so let's go back to, let me go back to sort of something over here. So this, let's go and analyze this union for a second. So remember, we did B is equal to B union G of I comma R of I. So we want, you'll see that we need this. We want to store the number, or technically I shouldn't say the number, the set of elements, or we need to store the size of the set of elements such that Ri is greater than equal to z. Now we're not storing the elements, we're storing the hash. There's a problem that two elements, two different elements I prime have Ri is equal to Ri prime, which is greater than equal to Z, but G of I is equal to G of I prime. Right? So there could be a collision under G which affects the count of the number of elements such that R of I is greater than Z. Right? Does this make sense? Right? This is going to be a problem. So we need G to map to a large enough universe to prevent collisions. How large does that universe need to be? Now, at any point, we ensure that the number of elements with R of I greater than Z is at most C over epsilon square. So this in some sense is ensured by the fact that we keep reducing the size, right? So whenever we have a value of Z, the number of elements I should say seen so far. Now I'm being a little informal here, but intuitively you can see why this should be true. So as long as you don't have too many collisions, when you're tracking the size of B, you are genuinely tracking the number of elements with Ri greater than Z. So since we see at most C over epsilon square elements, by randomly mapping to a universe of essentially that square, I'll say maybe omega of that, we ensure no collisions, with high probability. Indeed, if we set the universe, this universe, right? So what is this universe? This is, remember, G is mapping this to some universe. This is the universe that I'm talking about. To be at least of size, C square over epsilon to the fourth times some log n factor. We can ensure collisions happen with probably at most something like 1 over log n. You can put you can put some extra factors of C over here, and you can ensure something like C log n over here. So collisions happen with very low probability for a given Z. You can ensure for a given Z, collisions happen with low probability, and then union bound over all the z to ensure that for all z, collisions happen with low probability, right? Because the number of z that we're going to see is actually, it's going to be at most log n. That's how many different values of z we're going to see, because we're going to keep increasing the value of c. And so as we keep increasing the value of c, we can ensure that collisions happen. And for this, pairwise independence suffices. So I'm not going to write out this proof over here, and I'm going to leave it as an exercise for you to sort of work out the details. They're pretty much following exactly this analysis, this logic. The specifics of this, which is sort of the key, this is essentially doing the birthday paradox analysis that we did with the variance calculation that we had, and you can see that their pairwise independence suffices, and so for that we can get this analysis to work. So any questions about this part, like why the universe size is sort of set to, why this universe size for G suffices? Any questions on that? Okay. Now, because let's just go ahead and assume that these collisions don't happen, in which case we can assume that B stores I directly. Right? So we can assume that what B stores over here is, let's just assume that B is just going to store the element exactly, in which case R of I can be computed on demand. And so B is just storing the set of elements. And this is going to make our math, make our calculation simpler. And in the formal proof, what you would do is you would say this holds with high probability, and then eventually do a union bound over all the errors. All right, so let me move these out of the way. Okay, so I'm also going to assume full independence, and you can do pairwise independence and essentially you have to replace a Chernoff by a Chebyshev. I'm not going to do that. I just want to show you the basic idea, for which it's just convenient to think of the hash function values being fully independent. Okay, so let's assume that B stores I directly. Let's consider the indicator random variable xli. This is the indicator for the event that R of I is greater than or equal to L. xli. Right? So I'm going to assume full independence on the xli's if in general you only need pairwise independence for this analysis to work. What is the expectation of xli? It's 2 to the minus L. Right? And this is something that we discussed before, because this is just the number of trailing zeros being at least L. Let's look at YLI. So what is YLI? YL. YL is the number of elements, so I in the stream. So the number of elements seen such that R of I is greater than L. So technically this is like the size of the bucket. This is what the bucket is storing. And so the expectation of YL is D times 2 to the minus L, right? Just by linearity of expectation, D is the number of distinct elements, and that is the number of summands. What is our estimate finally? Our estimate is 2 to the Z times B. Now remember that B is just Y of Z. It's the number of elements which have more than Z trailing zeros. And we're trying to understand what is the probability that the deviation is more than epsilon times, the true value. Okay, I'm going to simply I'm going to just divide this expression by 2 to the Z, So I get, what is the probability that yz minus d times 2 to the z is greater than epsilon times 2 to the minus z? Oh, but d times 2 to the minus z is exactly the expectation of yz. So in trying to understand the concentration of the output, I'm looking at the concentration of this random variable yz. So the probability that yz minus the expectation is at least epsilon times expectation, and we know that there is a Chernoff bound here. Right, so this is going to give you 2 to e to the minus epsilon square expectation of yz divided by 3, and there's a 2 over there because I did a union bound over the upper tail and the lower tail. Okay, so any questions about this? Is this clear? Okay, then let's proceed. Okay, so I want to keep this expression over here. Now we need to be a little careful, and you'll kind of see that this is where like the choices of various parameters come in. So if the expectation of yz is at least c over epsilon square, then yz concentrates. So it concentrates around its expectation. Sure. But if the expectation of yz is much smaller than c over epsilon square, then all bets are off. So what we need is we need to ensure that the final value of z in the algorithm, in the output, has, and let me refer to this as property 1, has property 1. So if we can ensure, remember that the algorithm, and just to sort of show you the algorithm, remember that the algorithm is going to sort of initialize z to 0 and then keep updating z. When it outputs, it's going to have some value of z that it's storing. We need to ensure that that value of z has property 1. Okay, so is that clear? Okay. So let's try to understand this event. So let's do it now. Let's do it somewhat formally. Let 2 to the L be well, actually, okay, let me write this out separately. Let L be equal to maybe the ceiling log base 2 epsilon squared d over 10. This is going to just be a convenient parameter. What I will want to show, okay, so let's actually see what I'm going to show. So I'm going to say the probability over the union of L at most, sorry, let me give this a different name. I don't think I've used K as of yet, so I'll call this K. So let us look at the following events. Okay, the probability of this, and I'll say that the event that y of L minus d times 2 to the minus L is more than epsilon d times 2 to the minus L. So what I'm saying is, let me fix some value of k. So log base 2, so essentially the log of epsilon squared d over 10, and you'll see exactly where this expression is going to come in. So I'm looking at the event that for some L that is less than k, y of L deviates too much. Okay, so this is the event. So what is this? Event that there exists L less than k where y of L deviates too much. Okay, now I just use union bound here. So I replace the union with a sum. So I'll say the sum of L being at most k, and just using my Chernoff bound calculation, it's e to the minus epsilon square times the expectation of YL divided by 3. Now, what is the expectation of YL? It's d times 2 to the minus L. Now, I chose L to be less than k. I chose L to be less than k. And therefore, I can, maybe instead of a ceiling here, let me put a floor. So I can ensure that this is going to be at least d times epsilon squared, d times 10 divided by epsilon squared d, which is 10 over epsilon squared. So for all L that are less than k, the expectation is at least 10 over epsilon squared. Okay, is that clear? So another way, let me just plug these values in over here and say that summation L less than k e to the minus epsilon square d divided by 3 times 2 to the L. Now essentially this is decreasing essentially doubly exponentially, you know, as L increases, so 3 times 2 to the L. So this is essentially, it's dominated. It is dominated by the largest term, and the largest term happens when L is equal to k. So this sum is dominated by the term L is equal to k. And sort of, I'm not going to do the math in gory detail, but you can basically show this is at most like 1/10. Okay? And that's because we know that for all values, d times 2 to the L is at least that much. Formally speaking, what you can show is d times 2 to the minus L. You write this as d times 2 to the minus k times 2 to the k minus L. This is exactly that, and then you get like you'll get something which is essentially bounded by geometric progression, and you can get this math to work. And so what this says is that for all L that are at most essentially log of epsilon squared d over 10, we get concentration. Okay, so is this clear? Any questions? Okay. Now let's look at the event that L is greater than k. Let's look at just the event that the final value of z is going to be greater than L. Well, this is simply just the event that z is greater than k. Right? And remember that k was log square was log of epsilon squared d over 10. So this is the event that that z is going to be greater than k. Now this is essentially the event that y of k is greater than or equal to c over epsilon square. This is a random variable, so this is well defined. So when is z going to be larger than this? That is going to only happen if we saw enough elements which had at least k trailing zeros. And by enough, it's c over epsilon squared, because that's the only way that the algorithm will select z to be more than k. Okay, is this clear? Questions? Okay. So now what we do is we need to understand what is the probability that yk is going to be large. Now we'll just use Markov. So we'll say, what is the expectation of yk? As we discussed, this is d times 2 to the minus k. So this is d times, essentially you get 2 to that quantity over there. So we'll say that it's epsilon squared d. Essentially, it's epsilon squared d over 10. Right? I'm probably missing like a floor or ceiling. No, actually, so then this is fine. So this is at most that quantity. Sorry. Okay. I'm sorry. My apologies. I'm messing this up. So this is at most d times 10 divided by epsilon squared d times 2 because of the floor. And so what I get is that the expectation is at most 20 over epsilon square. So then by Markov, so I just use Markov here, this probability is going to be at most 20 divided by c. So let's set c to be like 100. So what this means is that the probability that z is going to be strictly greater than k is at most 1/5, and then the probability that y, so we can say for z at most k, the probability that y of z minus 2 to the minus z is greater than epsilon d times 2 to the minus z. This is at most 1/10. So by the union bound, with probability at least 1 minus 1 over 5 plus 1 over 10, so this is at least the probability at least 2/3, z is less than k, and the estimate is a 1 plus approximation, 1 plus epsilon approximation of d. And that ends the proof. Okay, so there are sort of a number of moving parts here. First was, of course, the birthday paradox calculation. But having that aside, there are two parts to the argument. The first part, which is sort of a routine Chernoff bound and union bound argument, simply says that if y of z has a large enough expectation, then y of z is going to concentrate. Secondly, we argue that the z is chosen such that this will happen, because the probability that z is going to be larger than some threshold k is at most 1/5, or we can sort of tweak these constants here. And so this then ends the proof of this algorithm. Any questions? Any questions? Okay, if not, I'll continue. And I'm going to do a short diversion, maybe just at most like 15-20 minutes, on hash functions and this notion of 2 universality. So let me define a family H of functions. So let me write this out, somewhat abstractly. So let's write it out as follows. So you have, so this is some H to some universe. Okay, these are hash functions, and we'll think of the universe size is at most n, is a 2 universal family of hash functions if for all x not equal to x prime and u prime in U, the probability over choosing H at random from H. So H is chosen uniformly at random from H. So you can think of H really as the distribution, and so somewhat abusing notation, I'm going to say that H is drawn from this distribution, which is just the uniform distribution on hash functions. The probability that f of x is equal to u and f of x prime is equal to u prime is exactly 1 over u squared. So what this is pairwise independence. So a 2 universal family of hash functions gives pairwise independence. And the question is, how do we construct such a family? Can we construct an explicit family which has this provable property? And when you have k universal, typically you have k-wise independence, where you have k elements in your domain, k elements in the range, and you look at what is the probability that each one of them is mapped according to the bijection between them. Now, the important point about 2 universal families is in all the algorithms, in all the analysis that we have previously done, we can actually replace the hash functions by a 2 universal family. And this will then give, a completely provable algorithm. So any questions about that? Do you understand what a 2 universal family is? So you cannot use the Chernoff bound. You would instead have to do Chebyshev. But all the proofs will go through. Like actually, it's pretty much the exact same proof method as shown. The only difference is whenever there's a Chernoff bound, you replace it with Chebyshev. This will of course give you weaker guarantees on the probability, but actually the math is robust enough that those weaker guarantees suffice to get all the error bounds to work. Okay. Now let me describe to. Go on.
In general, if we had like a k universal one, we could use like a case moment method.
Basically, if you had a k universal, you can go up to the kth moment. So let me give you two universal families. I'm not going to prove them. I'll leave the proofs of exercises. They're not particularly difficult. The first one is actually not the most efficient one, but I think it's instructive to see. The idea is to use random projections. So let us treat our domain as really bit strings. So let's just assume that n is a power of 2 for simplicity. And I'll basically treat this as an element over f2 to the log n. Right? So this is the finite field with 2 elements. So now suppose let M be a matrix, which is just going to map log n cross log of u. Right? So the idea is that we essentially treat every element. So this is a domain element. This is something in n, which is essentially a log n bit string. So we'll multiply it with this matrix, and you can think of the matrix as going to be log n cross log u, and then this is going to give me my hash value. This is going to, so if this was x, then this is h of x, which is now an element, although it's basically, I think of it as a bit string or over the finite field. And so we can think of what h of x is just m of x, and m is chosen with uniform at random independent entries in f2. So this is the family. So to construct your hash function, you basically construct a random matrix, and now you'd use this mapping. So this family is 2 universal, but it requires log n times log u bits to store a hash function, because you have to store this random matrix. So it's not the most efficient, but on the other hand, I want you to see this idea. I want to present this idea to you because it's a very powerful idea, and it's something that we've seen multiple times, the power of doing random projections. And by the way, just to be clear, all the algebra is over the finite field. Right? All the algebra is done over f2. Okay, so this is one family. An exercise is to prove it's 2 universal. Prove it is 2 universal. A more efficient method in sort of, I guess, in all ways, is to instead use some kind of finite field algebra. So now again we will treat this. Now will be a little different. Instead of treating it as vectors, we will treat this as essentially the finite field with n elements. So again, you'll have to round n to make it a power of 2. But then you can treat this as a finite field. So there is some kind of algebra over there. And this mapping is done arbitrarily. It's not important how you actually map the elements over here to here. So remember, we assume n is a power of 2. Now how is the family chosen? So we choose A and B uniform at random in this field, and h of x is basically just going to be ax plus b, but truncated. So we'll say it's actually the last log u bits of this. Right? So you do the algebra in the finite field, and then you just truncate and you show the bits. this is a little more challenging as an exercise, but this family is too universal. Okay, and just as a hint, I'll say consider x prime, say x not equal to x prime, and y prime, such that now these are again all in the finite field, such that ax plus b is equal to y, and ax prime plus b is equal to y prime. So this is like this is sort of the event that you're looking at when you're discussing two universality. And this will happen if a and b are chosen to simultaneously satisfy these equations. And so by finite field algebra, there is a unique choice of a and b satisfying these equations. So the probability that ax plus b is equal to y and ax prime plus b is equal to y prime is exactly going to be 1 divided by n squared. But we're doing a truncation. So then you have to sort of go over this a little bit more carefully, but there is a truncation. So what does that mean in terms of the two universal definition and these equations? And so this you'll have to figure out, but once you figure this out, you'll see that essentially the core is this fact over here, that there's a unique choice of a and b that satisfy these equations. So I'm not going to, as I said, I'm going to leave this as an exercise, but the important point here is it only needs 2 log n bits to specify a hash function. You only need 2 log n bits, right? So we need 2 log n bits to store a hash function, a 2 universal from a 2 universal family. So this adds O of log n to all the bounds above. Right? So if you wanted to actually consider what it takes theoretically to store a hash function to use, then it adds an O of log n, which clearly subsumes all the log n and the log n over epsilon square, but nonetheless often the bounds are written so that this storage is just to generate the hash function, the remaining is the algorithm itself. And of course, if you assume the more realistic model where hash functions exist, then this storage is not needed. So at this point, I'll pause. Let's take a slight break, and I will answer any questions you have about this, because after this I'll move on to another topic. Let's continue with our next topic. And this is, so we did distinct elements, which is like one of the classic important problems. There's another one which is called finding heavy hitters, or frequent elements. So find the elements in a stream that occur frequently. And you can imagine this also has similar applications. A lot of it initially did start by looking at traffic data. That is, if you have a router which is looking at lots of connections, you're trying to store the IP addresses or maybe the other routers that send the most connections. So it is useful here to sort of give two models here. So this is my stream, and then there's some element that I'll call x, and x appears multiple times. So this one can think of the insertion only, insertion or increment only, and this is often called the cache register model. So this is the model that we've been talking about so far. You get elements in a stream, and they get inserted. You're just looking at how many come. There is the increment and decrement. So this is the more general model. The increment and decrement. And the increment and decrement is also called the turnstile model. So here we think of the stream has pairs x, c. So x is the element, and this is a count, and the count can be negative. The count can be negative. And just to sort of put this out there, the strict turnstile model just says that the total counts are always positive. Always. So for this reason, it is going to be convenient for me to think about what I call the frequency vector f, where f of I is the total count of element I, in n. Okay, so again, our universe is n. We're seeing elements come by, but we can also, in the turnstile model, we could see them with counts which can also be negative. In the insertion only or the cache register model, you only just see, it's just sort of a stream. You could think of just connections. But in the increment and decrement, you may think of some kind of counter which can be incremented or decremented. And the reason to bring these up is typically when one is thinking of distinct elements, one doesn't really get into these models as much, but for counting heavy hitters or frequent elements, this makes a lot of sense, because what's interesting with the increment and decrement, the turnstile model, is there could be an element whose frequency goes up, but then whose frequency comes down, whose count comes down because of a lot of decrements. And the question is, can the algorithm handle such kinds of operations? So what is the style of the bound? So we'll see the style of the bound is we'll typically say store O of k elements, or k is going to be a parameter. Store k elements, O of k or k log k, or some, generally this is going to be some function of k, maybe not O of k, some function of k. Now each element requires log n bits. So the storage is going to be of the form O, some polynomial in k, log n. And maybe there's an additional log m, where m is the stream length. So but you can think of it as just storing k elements, store k elements, and find all elements with frequency at least m over k. So this is the style of the bound that we're looking for. Find everything that appears with probability at least 1 over k in the stream. If you were to think of sampling uniformly at random from the stream, and store k elements. So by storing, I don't know, just 100 elements, you want to find everything that appeared more than 1% of the time. Okay, so is this clear? Any questions on the specific setting of the bounds?
So how do you get this m?
How do you, so you don't know what m is beforehand. It's a good question. You don't know what m is beforehand. You may not even know what n is beforehand. So you can think of it more as a percentage, right? You want to basically find everything that appeared more than 1% of the time. If you wanted to store m, you could store m, right? You could just keeping track of the total count.
So is this meant as like a means to an end to answer the previous problem, where you have increments and decrements? Or
I'm just telling you what is the style of the final bound that we're going to get. And I sort of abuse notation here. I'm being a little unclear. So there are multiple things that I should maybe be more precise on. Let's just say that I want the 1 norm divided by k. So the 1 norm, so think of f is this vector of counts. Vector of counts or frequencies. A heavy hitter is everything whose count is at least 1 over k times the total, and you want to find all the heavy hitters, right? So a heavy hitter has f of I being at least the total of I divided by k. That's a heavy hitter, and you want to find all the heavy hitters in this stream, in the streaming setting. So does the problem make sense? And what I mean by here, this is the kind of bound that I'm hoping to get. Okay. So now let me start with a very simple solution, a very basic idea, and I'll demonstrate a very beautiful fact about sampling from streams called reservoir sampling. So the basic solution, and let's just think of the cash register model. It's very simple. You're just seeing items come one by one. Suppose we can sample a uniform at random element in the stream. Now be careful. What I mean by uniform at random element is not a uniform at random element from what has been seen so far, but rather a uniform at random element in the stream which has multiple copies of the same element, right? So this is going to sample an element proportional to f of I, right? This is simply saying that the probability of sampling I should be f of I divided by m, right? And because m in this case is simply going to be the 1 norm, because it's the cash register model, right? So this is essentially doing that. So clearly, if we sample, let's say O of k log k, and maybe here, yeah, O of k log k, uniform at random elements, we are guaranteed to find all elements such that f of I divided by f is at least 1 over k. which is equivalent to saying that f of I is at least that. We're guaranteed to find all the elements such that this is true, right? And you can union bound over all the k heavy hitters to complete the proof. So this is a good exercise in Chernoff bounds. Exercise in Chernoff bounds. Of course, this is assuming you can sample a uniform at random element from the stream. So if you can sample a uniform at random element in the stream, then the probability of sampling I should be basically proportional to the frequency of I. And if one can do this, then one samples k log k elements. We are guaranteed to find all elements such that we are guaranteed, I should say, with high probability, we're guaranteed to find all elements. So you have to do a Chernoff bound for each heavy hitter and then a union bound over all of them to complete the proof.
But you might also find some elements that are not.
Good point.
Like we have to do the same thing that we do with coupon collecting, where you like do it multiple times and see how many like have at least 2 appearances.
Good point. So what you could do is that's a good point. So I was hoping not to get into that discussion, but since you've brought it up, so no, that's good. That's a good observation. So the point is, what you could do is instead you sample these many and you only report the elements that have been seen sufficiently many times, and then you use the Chernoff upper and lower tail. So okay, so maybe this is worth saying. So the final guarantee is of the following form, which you can think of also in terms of this precision and recall type methodology, which would be report. So report any element. So report all elements such that f of I is at least, I'll say maybe, and do not report any element such that f of I is less than, where the 2 is just a constant for convenience. You can replace this by anything that is more than 1. Right? You could replace this by 1 plus delta and put a 1 plus delta there. And so the final guarantee is we will report every element that is seen a little bit more than f over k. We guarantee that we'll report all of them. We will never report anything whose, again, like I wouldn't say never, so then with high probability, both of these will hold. And this can be done by you sample these many elements. You only report the elements that have been seen sufficiently many times. What is that sufficiently many is, again, an exercise in Chernoff bounds, and it'll tell you what the answer is. So does that sort of answer your question?
Yeah, exactly.
Yeah. And this is again sort of like a precision in recall, right? Because you have this two-sided guarantee. So what this says is you will report everything that is sufficiently interesting, and you will not report anything that is sufficiently uninteresting. Right? So this is like recall. You get everything that's important, and this is precision. Right? You don't report things that are unimportant. Okay. But let's go back to how can we sample a uniform at random element from the stream? And it's unfortunate that I should do this in the last 5 minutes, but this is really beautiful. This is really a work of art. And some of you may have seen this before. This is called reservoir sampling. And this was introduced by Witter in '85. It's amazingly simple. It's an amazingly elegant algorithm to sample a uniform at random element from the stream, and it simply stores one element. That's all it's going to store. It's going to store one element. So here's the algorithm. On seeing the tth element in the stream. So I'm just going to refer to the stream as S, and I'll say this is S of t. Right? This is the tth element of the stream. So the algorithm is simply, on seeing the tth element of the stream with probability 1 over t, replace the stored element by S of t, and with the remaining probability, probability is essentially do nothing. So this is it. On seeing the tth element of the stream, you replace whatever you've stored with that tth element. Now with the remaining probability, do nothing. That's the algorithm. So let's look at what is the probability of finally ending up with S of t. So this is the product of the following. So firstly, it doesn't matter what happened up to t steps. So you have the probability of picking S of t at the tth step times the probability for all time steps. So all time steps t prime that are strictly greater than t, going all the way up to m. So this is t prime going from t plus 1 up to m. The probability of not picking S of t prime. Right? So at this tth step, you have to pick S of t. And at all subsequent steps, you should not pick the next element, the S of t prime. Does this make sense? So let's write this out. What is the probability of picking this element at the tth step? It's 1 over t times the probability t prime going from t plus 1 to m of 1 minus 1 over t prime. Right? Because you have to pick it at this step and not pick at the subsequent steps. So 1 over t times, and I'm just going to write this as t prime minus 1 divided by t, right? T prime. So this is just the product of t prime going from t plus 1 to m of t prime minus 1 divided by t prime. Now let me plug in values here, or let me just expand this this out. So I get t plus 1 divided by t times t plus 1 divided by t plus 2 times t plus 2 divided by t plus 3, so on and so forth, until I get m minus 1 divided by m. And lo and behold, all of these terms cancel out, and you end up with 1 over m, which is exactly what you wanted. It's a uniform at random element from the stream. So the probability of finally ending up with S of t is independent of t. It's only 1 over m. And so this is reservoir sampling. And so, frankly, if there's nothing else that you take from today's lecture but reservoir sampling, I think it would still be a success. So reservoir sampling is this amazingly simple and elegant technique using which you can sample a uniform at random element in the stream. And what you get is you can effectively, with some Chernoff-bound calculations, you can report all elements that occurred sufficiently often. Now it turns out that there's actually a deterministic solution. Which is also an immensely elegant algorithm of Mishra and Grace. And Mishra and Grace is, I believe it's the 80s. It's 82, which is, in some sense even better. It's deterministic. It's only O of k log n bits, whereas we used k log k. And this is a deterministic solution, which is even better. But it's a very clever algorithm. I won't get into Mishra-Grace. Instead, in the next lecture, I want to come to what are called sketching solutions for the problem of finding heavy hitters. And I'll talk about the count-min sketch, which is a very nice solution for that problem. So with that, I'll end, and I'll take any questions.